Okay. Good morning, ladies and gentlemen. My talk will be about close-range photogrammetric digitization and web visualization of small-scale known ferrous artifacts. The work presented here was not only carried out by myself, but also by my colleague Stefan Eichert, who is very sorry he cannot attend this conference. The objects we digitized are mainly Avarian period belt fittings found not far from here at Lani Castle in the Thaya floodplains. These tiny objects are only a few centimeters in size, and many or most of them are perforated. They are made from known ferrous metal, and mostly they are very shiny and glossy. So to speak, creating high-resolution 3D models of these kind of items is a challenging task. Of course, you could ask, and you should ask, why do we need to scan them at all? Well, to begin with, I have to tell you that our research work is carried out within a cross-border project between Austria and the Czech Republic. So, having a virtual replica of these objects allows every team member to have access to these objects, and we can use and we can apply any metric data analysis and can do further analysis in the future. And in this case, it is very important to have these digital copies, because we have only a limited access to the items, because most of them are private property. And finally, having an interactive 3D model makes these items much more comprehensible for both for researchers and for the public. To make these models more accessible, we decided to put them online. Is the internet working now? I don't know, I have to check. I don't think so. Okay, the internet is not working, unfortunately. Okay, but we created a 3D web viewer, which we implemented in the project homepage. The viewer consists of a rondel where you can choose and you can select the model of your choice, and you can change from standard to high definition. And when you click on an item, you get additional information, and the model itself can be, of course, moved and zoomed in interactively, and the viewer can be enlarged. So on the next slide, can be enlarged, and you can change to different kinds of visualization. So you can have a texture model, or a point cloud, or a wireframe, or this shaded model. But now let's go into details about how we created these models. First of all, we wanted to apply an image-based approach because structured light scanners are still quite expensive, and we were low on budget and wanted a low-cost solution, of course. And our aim was to do some kind of proof of concept that you can scan small and shiny objects using an image-based approach. This was already done by our colleagues Benjamin Stuhler and Zeta Stuik, who scanned these earrings from Krain. However, they used the shape from silhouette method, which worked quite well, but which is very limited in resolution, and which is not suitable for the recording of concave surfaces or undercuts. They did not use the much more complex and much more famous structure for motion and multi-view stereo approach, because they had problems finding enough feature points at the narrow parts of the objects. As our objects are not that narrow, we tried to apply structure for motion and multi-view stereo algorithms for model creation. Most of you probably know this kind of figures. It's a screenshot from the software Argisoft Photoscan, which we used to calculate the models. So the software is able to automatically reconstruct the 3D geometry of a scene from a series of overlapping images using the parallax effect and triangulation. How this works in detail is not addressed in this talk, and I think it was explained in numerous papers before. Here you see our workspace or scanning workspace. Well, we are using a simple light tent and a manual turntable. And by spinning the turntable, we get about 24 to 36 different camera locations for each orbit. The exact number depends on the object. The narrower the object, the more camera locations you need. By turning the object, you can create another orbit, and you need at least 2 orbits. 3 are better to guarantee for a reliable image alignment, because in this way, when you have 3 orbits, the angles between the orbits is not so large. When you take close-range pictures of very small objects, of small and shiny objects, you're facing 2 main problems. The first problem is the objects are small. The second problem is the objects are shiny. And well, this means you need a well-adapted illumination, and you need to think about how you can increase the limited depth of field. Both shininess and unsharp pictures can introduce a serious noise to your captured dataset. To reduce the overall shininess, we used very diffuse illumination conditions and low light, which forced us, of course, to use long exposure times. Also, every item was individually shaded in each camera position to kill shininess on very exposed parts of the object. Another approach would be to apply a coating, like a powder or something, to the surface. However, this can only be done if it's absolutely certain that the powder will not leave any residue on the object or cause any damage to it, either at the moment of application or in the long term, which is why we didn't use it. We also didn't use polarization filters, because the light reflections of metal surfaces are not filtered by polarization filters. Gabriel Guidi et al. Already experimented with polarization filters, and their results are confirming this effect. As you can see, the number of points is even lower when you're using a polarization filter. This is not true for shiny ceramics, where the polarization filter works quite well. To overcome the very limited depth of field, we figured out the sweet spot of our camera lens combination. The sweet spot is where these 2 graphs are touching each other. Let me explain. It's probably well known that the higher you set the f-spot of your camera, the more depth of field you get. But this is only true up to a certain point, when the increased depth of field is counteracted by blurring due to diffraction. Diffraction is when light, or when a wave, it occurs when a wave encounters a narrow point and is bended around the corners, and in this way the obstacle distracts the light and makes the image blur. Finding the sweet spot is important, but the received depth of field is still way too small for an overall sharp image, as you can see here in this picture. In this picture on the left side, the background is sharp, and on the right side, the foreground is sharp. That's why we applied a technique called focus stacking, or deep focus fusion. Focus stacking is a digital image processing technique which combines multiple images taken at different focus distances to give a resulting image with a greater depth of field than any of the individual source images. This is a focus stacked image of 13 pictures. Above you see only the very first and the last picture of the focus series. Basically, focus stacking works similar to high dynamic range imaging. And to have an control about which part of the image is actually in focus, we're using an app called QDSLR Dashboard, which acts as a remote control for the camera, and it's working via Wi-Fi. And the app supports a feature called Focus Peak, and is coloring the part of the image which is actually in focus. Okay, now we finished the part of data acquisition and we move over to data visualization. Despite the fact that we are creating 3D models, they can be displayed two-dimensionally, of course. And here's just one example of how an illustration for a printed publication could look like. This kind of illustration makes sure all objects are displayed in the same way, using the same standards, and are not dependent on the skill of the drawing person. Now we are going digital and 3D again. We all know the problems of big files, which are hard to handle with, which becomes a real problem when you are presenting these big files online. The internet is all about seeing visual information instantly, and waiting time for a 3D model to display is a no-go, and therefore it is necessary to compress your data, and we converted our 3D models into OpenCTM format, which compresses the geometry lossless to a fraction to comparable file formats, like you see on this picture. And OpenCTM format also supports the most important features, and like vertex color, texture coordinates, and big meshes, and is therefore ideally suited for storing 3D information. Now we are finally back at the very beginning of the talk to our 3D web viewer, which was where we implemented our 3D models in our project homepage. And we were looking for a web viewer which we could implement in the homepage and which we could customize. And we came across this JS3D viewer. This viewer is built on JavaScript, and the rendering is using 2D canvas technology, as well as an optional WebGL backend that provides more efficient rendering if needed. It is designed to be widely compatible with most major browsers that support HTML5 canvas. Yeah. And if you'd like to take a look to the viewer for yourself, here's the link again, and you can also use this provided QR code. And at this last slide, I would like to summarize. So we presented an image-based and low-cost approach to digitize small and shiny objects and highlighted a modern way to offer archaeological context to a wider public on the internet. Almost all steps in our workflow are using open source software besides Archisoft Photoscan, which can be replaced by open source software, of course. But the drawback of our chosen approach is that data acquisition and data processing is quite time consuming. You need some photographic and coding skills, in our opinion, when you want to scan a very large number of these artifacts, it could be worth to try structured light scanners as well. Thank you for your attention.